In this video, we shall see the main electrical components that are present in all power electronics used to convert direct current and alternating current. These components are four: the switch, the inductor, the flyback diode, and the smoothing capacitor. Then, once we understand how these components work, in the next video we shall deploy them in various topologies. First of all, we need switches, which are designed to turn on and off rapidly, from 10 to hundreds of kilohertz. These frequency ranges currently gives a good compromise between a harmonic distortion, reduced size of passive components, electromagnetic interference, and switching losses. Traditionally, conventional thyristors were used as switches. Thyristors are electric components consisting of three p-n junctions, which operate as bistable switches. One disadvantage of these components is that the thyristors cannot be turned off, but only turned on by applying a signal to the gate. Such switches lead then to a very high harmonic content, requiring additional filters in order to make the output compatible with the electrical grid. A special type of thyristors used nowadays are the gate turn-off thyristors, which are fully controllable because they can be turned on and off at will. Thyristors are only used for inverters with a power of 100 kilowatts and above. There are other types of switches that generate an output with little harmonic content and that are fully controllable. The most popular technologies are insulated gate bipolar transistors, or IGBTs, and metal oxides semiconductor field effect transistors, or MOSFETs. So when you have to design a new inverter or converter, it is better to see what are the properties of each switch in order to make the most out of them. In fact, the best choice is a trade-off between fast operations and energy losses, which can be easily calculated for each type of technology. The next component is the inductor. Simply speaking, an inductor, or a coil, is an insulated piece of wire wound around a magnetic core that serves to store energy in the form of magnetic field. To understand how an inductor works in a circuit, we will use the following example. Here we have a battery or a power supply, a light bulb, and a switch. In this simple circuit, if you close the switch, then the bulb lights up. However, when we place a coil in parallel to the light source, the circuit behaves differently. First, note that the light bulb is basically a resistor, and this resistance creates a heat to make the filament in the bulb to glow. Also, the wire in the coil has a resistance, but it is much lower than that of the light bulb. When we now close the switch, the bulb turns brightly and then dims down. This is because at the beginning, less current flows in the coil, which is building up a magnetic field, resulting in a repulsive electromotive force, depicted here in orange. While the field is building up, the coil restricts the flow of current, but after a certain amount of time, the energy is stored in the magnetic field, and almost all the current flows to the coil. Then, when we open the switch, what happens is that the bulb burns very brightly and then quickly goes out. The reason is again the inductor. For some time, the magnetic field stored in the coil keeps current flowing through the coil and hence through the bulb. The current flow through the bulb dissipates the energy that was stored in the coil, causing the magnetic field and hence the current to drop until the field vanishes and the bulb turns off. In other words, the inductor stores energy in its magnetic field and it tends to resist any change in the amount of current flowing through it. This type of behavior is given by this first-order differential equation, where the voltage across the inductor is proportional to the derivative on time of the current that flows through the coil. And by calculating this current, it is also possible to calculate how much magnetic energy is stored in the coil. The third component that we introduce is the flyback diode, extremely important for the converters. It is a diode used to eliminate flyback, which is the sudden voltage spike seen across an inductive load happening when its supply current is suddenly reduced or interrupted. Let's see this problem in detail. In its most simplified form, a voltage source is connected to an inductor with a switch. In steady state, with the switch closed, the inductor has become fully energized and it is behaving as a short circuit with current flowing down from the positive terminal to the negative through the inductor. However, in the moment that we open the switch, The inductor will attempt to resist the sudden drop of current by using its stored magnetic field energy to create its own voltage. Hence, an extremely large negative potential is created across the inductor, and the voltage at the switch becomes the sum of the voltage of the power supply and the voltage of the inductor, generating a very large potential difference that can cause electrons to arc across the air gap of the open switch. Problems might occur when the switch is very fast, so you have in a very tiny amount of time that the derivative of current becomes very high. This can be potentially dangerous since if there is necessary environmental conditions are met, you could even have a spark. A flyback diode solves this starvation arc problem by placing it in parallel with the inductor. When the switch is closed, the diode is reverse biased against the power supply and does not exist in the current for practical purposes. However, when the switch is opened, the diode becomes forward biased relative to the inductor, allowing it to conduct current in a circular loop. So the current that was charged inside the inductor can still circulate in this topology without being eventually transferred to the air with an arc. So this is the concept of flyback diode, which is activated every time an inductive load is switched off. And finally, another important component is the smoothing capacitor, which is placed in parallel with the load. From all these switches, the resulting signal is periodic in time, but actually the output of a DC-DC converter has to be also a DC signal. So the solution is to place a smoothing capacitor, also called a reservoir capacitor, to smooth the signal. As the voltage of the signal increases, it charges the capacitor and also supplies current to the load. When it reaches the peak of the signal, the capacitor is charged to its peak value, and here the role of capacitor is evident because it starts to release the stored energy. So in this short gap of time, the continuous flow of current gradually moves to the next periodic pulse, filling the gap and allowing the load to be powered at all times without any interruption. To conclude this video, we have seen 3 different types of switches, how an inductor works, and the importance to use a flyback diode to avoid the voltage spike seen across the switch when we open the circuit. Lastly, we also introduced the capacitor, which is used to smooth out periodic voltage signals. In the next video, we are ready to see the first topology of a DC-DC converter, which is the buck converter.